Okay, so next paper is paper 5 and its year is October-November 2019 and the variant is 5.2. So question is, a student investigates the maximum height reached by the light plastic ball when it is launched from vertically from the compressed springs. Look, this is spring when it's compressed due to elastic potential energy, right? It rises up. So elastic potential energy becomes the potential energy. So this elastic potential energy and this is potential energy similar to the MGH. And the question is, we have to design the lab experiment to test the relation between H and X. And then we have to explain how your result could be used to determine the value of the rho, which is density. Look, first of all, we have to write the definition of the problem. Compression in the spring X is the independent variable and height H is dependent variable and diameter or the radius of the ball is kept constant. So this is actually the definition of the problem. Next, we have to draw this diagram. We have to copy this. The ball is placed at the top when it is compressed down. So we can measure the compression from center to center. This difference is X compression. When it is released, ball rises up and this height can be measured by vertically clamped meter rule. For the diameter of the ball, for the radius of the ball, we will use caliper, but we have to measure also the K. For the K, we will load the spring with known load, and by using formula F is equal to KE, K spring constant can be measured. This diagram must be labeled, and then we have to write the procedure. Apparatus is assembled as shown in the diagram. The spring is compressed after placing the ball on its top. Compression X is measured for the reading of meter rule, R2 minus R1. Spring, the ball is released. Height of the ball, H, which is gained by the ball, is measured with the vertically clamped meter rule. Whole procedure is repeated with the different compressions X and its corresponding value of the height H is measured. Same ball is used to keep the radius diameter of the ball constant. Radius of the ball is measured from the vernier caliper and the spring constant is measured by formula K is equal to F over E, where E is the extension in the ball. Okay, next, after this procedure, we have to write the tabulation. First, number of observation, then compression, X, then ball height H1, then H2 in centimeter, H average, and then we have to measure X square, or we have to write the X square in centimeter square, right? Then the data analysis, this equation given, make dependent variable subject of the equation. So H is equal to 3K over 4 pi R cube rho G X square and y-intercept is 0. So when X square plotted at the x-axis, H at the y-axis, straight line passing through the origin. So this portion is the gradient. So if the graph is a straight line passing through the region and the gradient is 3K over 4 pi R cube rho G, then the relation is justified, okay? And the density rho can be determined by using equation. This rho is equal to 3K over 4 pi square G R cube into gradient. Radius is measured from vernier caliper and the K is measured from the spring load, F is equal to K. Next, we have to write the safety precaution. For the safety precaution, use a large box to collect the dropping ball which may hit the person, which may hit the observer. And the next, we have to write about the improvement, good design features. First one, rule must be clamped vertically with a bench. Measure the diameter of the ball in different directions, different orientation, and then calculate the average. Use a slow motion video camera to get H accurately because the ball does not stop at the height. And the next, avoid all sources of the draught by switching off the fans, etc., which may affect the vertical height gained by the ball. So this is question number 1. Now come to the question number 2. It's simple. Resistance R is equal to E over I, R is equal to P T power Q. by taking the log both side, we can write this equation. Log R is equal to Q log T plus log P. So when log T plotted at the x-axis, then the Q will be the gradient and this log P y-intercept. So 1 mark part. Next part is we have to actually fill up this table. So first R is actually V over I. Voltage is given 9.4 plus minus 0.1 and the current is this 1 plus minus 0.1 milliampere. So by using formula R is equal to V over I, we can calculate all these values. You can write it in 2 decimal places. Significant figures are 3 significant figures, right? And this error can be calculated by using the formula. Delta R is equal to delta V over V plus delta R over I times R. For example, the first one, 0.1 divided by 9.4 plus 0.1 divided by 1 times 9.4, so it's 1.04, so approximately 1 or 1.0, right? And similarly, we can calculate all the errors. Now come to this log R. So this value is R, so 9.4, its log is 0.973, okay? So the rule is, while calculating the log, the significant figure here, 2, so we can take 2 decimal places or 1 better 3 significant figure. So all values can be calculated. Now further, uncertainty in the log. This is the best formula. Uncertainty in the log R is equal to log R plus delta R over R. Or you can write log R plus delta R minus log of R. So all uncertainties are measured. Then question is plot the graph. So this is the graph. So best fit line, worst fit line. One more thing, for the error bars, first calculate the error scale constant for the axis which has the error. So here y-axis has error. So number of the small boxes divided by difference of the reading. Suppose I take these 10 small boxes, difference of the reading is 0.1. So 10 divided by 0.1 is 100. Now it becomes very simple. Look, first, error scale constant is 100 multiplied by 0.05, so answer is 5. So the first box, error scale constant multiplied by error, it was 5, so 5 boxes up, 5 down. Similarly for the next 3, so 100 multiplied by 3, so next 3 boxes up, 3 down. So in this way we can draw the all error bars. Error scale constant multiplied by the error is actually the height of the bar up and down. And then either bottom of this last to the top of this first, these 2 points are joined for the worst fit line. Then you have to label the both lines. Look, this is the best fit line and this is the worst acceptable line. Select 2 points for the best fit and 2 points for the worst fit and calculate the gradient. Look, the gradient is first point, second point for the best fit line, y2 minus y1, x2 minus x1. So after calculation, it's coming minus 14.3, minus 14.103. And for the worst fit point, P3 and P4, 2 points selected on the worst acceptable line. So M is 0.7, 0.3, 2.48 minus this, so it's coming this. Now this is actually the best fit answer, and the difference of these two is the uncertainty. Now for the next part, we have to calculate the y is equal to mx plus c. So look, c is equal to y minus mx. So use these points. One of the point from the best fit line, the y is equal to 0.85 minus 14.1 and into 2.49. So this is coming 13.96. So 36.0. Next question is, we have to write Q and P. Q is the gradient and y-intercept is a log P. So P can be written as log 10 power C. So 10 power 36, we can calculate P. No unit required. And then R is equal to PT power Q. We have to calculate actually the temperature. So resistance given 15,000. So this is 15,000 10 power 3. divided by P value 1 into 10 power 36. We have calculated. And T and Q power is the gradient. So after calculation, we can calculate the temperature, which is 181. So this is a paper 5.